Right now, as you're reading this, something unimaginable is heading toward us. Not a rogue planet, not a wandering black hole, an entire galaxy, Andromeda, containing over 1 trillion stars, each one potentially with its own planetary systems, is on a collision course with our Milky Way, and there's absolutely nothing we can do to stop it. In approximately 4 billion years, give or take a few hundred million, these two massive spiral galaxies will begin their slow, inevitable merger. The night sky that humanity has gazed upon for hundreds of thousands of years, the constellations that ancient civilizations used to navigate and tell stories, the familiar backdrop of stars that has remained essentially unchanged throughout all of recorded history, will be completely and permanently transformed. Now, before you start building a bunker or planning your escape route, let me be very clear about something. This isn't the kind of collision you're probably imagining. When I say two galaxies are going to collide, your mind probably jumps to images of cosmic destruction, massive explosions, stars smashing into each other like billiard balls on a cosmic pool table. But that's not what happens. Not even close. Galaxy collisions are strange, beautiful, and in many ways counterintuitive. They unfold over timescales so vast that they make human history look like a fleeting moment. They involve forces powerful enough to reshape hundreds of billions of stars, yet delicate enough that most individual star systems pass through the chaos completely unscathed. If you could somehow live through the entire event standing on Earth and watching the merger unfold over millions of years, you'd witness one of the most spectacular shows in the universe. But in any single human lifetime, you might barely notice anything changing at all. Tonight we're going to explore this collision in detail. Not just what's going to happen, but how it's going to happen. We'll walk through the entire process from the first visible signs that Andromeda is getting close, through the initial contact between the two galaxies, the chaotic period when they pass through each other multiple times, and finally to the end state billions of years from now, when a completely new galaxy emerges from the merger. We'll talk about what happens to our Sun, what happens to Earth, what happens to the supermassive black holes at the centres of both galaxies. We'll discuss the burst of star formation that occurs when two galaxies collide, why that happens, and what it means for any planets that might be around at the time. And we'll explore the question that probably interests you most. Could life survive this? Could humanity, or whatever humanity might evolve into, witness this merger and live to tell the tale? By the end of this, you'll understand exactly what's coming. You'll know why astronomers are so fascinated by this event, and you'll have a sense of just how different our cosmic neighbourhood is going to look when this is all over. So settle in. This is going to take a while because we're talking about an event that spans billions of years and involves forces and distances that are almost impossible to comprehend. But I promise, by the end, you'll see the universe a little differently. You'll understand that even galaxies, these enormous islands of stars that seem so permanent and unchanging, are temporary structures that form, evolve, collide, and eventually fade away. Let's start with the basics, because before we can understand what's going to happen when these galaxies collide, we need to understand what exactly is going to collide. Our home galaxy, the Milky Way, is what astronomers classify as a barred spiral galaxy. Picture a flat disk, kind of like a dinner plate, with elegant spiral arms curving outward from the centre. These arms aren't solid structures, they're more like traffic jams where stars and gas clouds bunch up as they orbit. At the very centre of the galaxy there's a bar-shaped structure, a thick collection of densely packed stars that extends out from the core, and at the absolute heart of that bar, buried beneath layers of dust and gas, sits a supermassive black hole. This black hole, which astronomers have named Sagittarius A Arctic, weighs about 4 million times as much as our Sun. That sounds enormous, and it is by any reasonable standard. But compared to the total mass of the Milky Way, it's actually a tiny fraction. The galaxy as a whole weighs somewhere around 1.5 trillion times what the Sun weighs, and most of that mass isn't even in stars. It's in dark matter, an invisible substance that we can't see directly but know exists because of its gravitational effects. The Milky Way is roughly 100,000 light-years in diameter. To put that in perspective, a light-year is the distance light travels in 1 year, moving at 186,000 miles per second. That works out to about 6 trillion miles per light-year. So the Milky Way is about 600 quadrillion miles across. If you tried to drive across it in a car going 60 mph, never stopping, never slowing down, it would take you about 1 billion years. Our galaxy contains somewhere between 100 billion and 400 billion stars. That's a huge range, and the reason for the uncertainty is simple. It's incredibly difficult to count stars when you're sitting inside the galaxy you're trying to count. It's like trying to count all the trees in a forest while standing in the middle of it. The nearby trees block your view of the distant ones. The dust and gas between the stars absorb and scatter light, making it hard to see into the denser regions. And there are vast numbers of small, dim stars that are extremely difficult to detect even with powerful telescopes. Now, Andromeda is similar in many ways, but larger. It's also a spiral galaxy, though its spiral structure is wound a bit more tightly than ours. More importantly, it's substantially bigger. Andromeda is about 220,000 light-years across, more than twice the diameter of the Milky Way, and it contains roughly 1 trillion stars, possibly more. That's at least 2 to 3 times as many stars as our galaxy has. If you go outside on a clear dark night, far from city lights, and you know where to look, you can actually see Andromeda with your naked eye. It appears as a small, fuzzy smudge in the constellation Andromeda. It's one of the most distant objects visible to the unaided human eye, sitting about 2.5 million light-years away. The light you see left Andromeda 2.5 million years ago, when our ancestors were still learning to make stone tools. But here's something interesting. Even though Andromeda looks like just a faint smudge, if you could somehow see its full extent, if your eyes were sensitive enough to detect all the faint light from its outer regions, it would appear huge in the sky. It would stretch across an area about 6 times the width of the full moon. The reason we can only see a tiny bright core is because most of the galaxy is too dim for our eyes to detect. But it's there, filling a substantial chunk of sky, invisible to us but very much present. Both the Milky Way and Andromeda are ancient. The Milky Way formed about 13 billion years ago, less than 1 billion years after the Big Bang itself. Andromeda is approximately the same age. They've been neighbours, part of the same cosmic neighbourhood called the local group, for essentially their entire existence. The local group is a collection of more than 50 galaxies bound together by gravity. But it's not an equal partnership. The Milky Way and Andromeda are by far the largest members. Everything else is much smaller, mostly dwarf galaxies that orbit around the 2 big ones like moons orbiting planets. The large and small Magellanic Clouds, visible from the southern hemisphere, are examples of these dwarf galaxies gravitationally bound to the Milky Way. For most of their history, the Milky Way and Andromeda have been doing a slow gravitational dance. They formed relatively close to each other, they've been pulling on each other with gravity ever since, and they've been gradually getting closer. This is the inevitable result of how gravity works. It never stops pulling. There's no friction in space to slow things down. Once 2 massive objects are moving toward each other under mutual gravitational attraction, they're going to eventually collide unless something intervenes. And in this case, nothing is going to intervene. Astronomers figured out that a collision was inevitable by measuring Andromeda's motion very precisely. They used a clever technique based on something called the Doppler effect. You're probably familiar with this from everyday life. When an ambulance drives toward you with its siren on, the pitch sounds higher. As it passes and moves away, the pitch drops. This happens because the sound waves get compressed as the source moves toward you, and stretched out as it moves away. Light does exactly the same thing. If a light source is moving toward you, the light waves get compressed, shifting toward the blue end of the spectrum. If it's moving away, the waves get stretched, shifting toward red. Astronomers call this blue shift and red shift. In the early 2000s, astronomers used the Hubble Space Telescope to measure the motion of stars in Andromeda very precisely. They were looking for this Doppler shift in the light. What they found was that Andromeda's light is blue shifted. That means it's moving toward us. By measuring how much the light had shifted, they could calculate the speed. Andromeda is approaching at about 250,000 miles per hour, or roughly 110 kilometers per second. That sounds incredibly fast, and by everyday standards it is. It's about 300 times faster than a passenger jet. But in cosmic terms, where distances are measured in millions of light years, it's actually quite slow. At this speed, Andromeda covers about 1 million miles per hour, which sounds impressive until you remember that it has to cross 2.5 million light years to reach us. That's about 15 quintillion miles. Do the math, and you find that the collision is still roughly 4 billion years away. That's about the same as the current age of the Earth. So if you imagine Earth's entire history, from its formation to the present day, and then imagine that same amount of time passing again, that's when Andromeda will arrive. 4 billion years is an almost incomprehensible amount of time. All of human civilization, from the first cities to the present day, spans maybe 10,000 years. Human beings as a species have only existed for a few 100,000 years. Complex life on Earth has existed for about 600 million years. 4 billion years is longer than any of these by a massive margin. But here's what makes this even more interesting. When the galaxies finally do meet, they won't just collide once and stick together. Instead, they'll pass through each other, get pulled back together by gravity, pass through again, and repeat this process multiple times over the course of about 2 billion years before they finally settle into a single merged galaxy. Think of it like this. Imagine you drop a ball into a large bowl. The ball rolls down one side, up the other side, back down, back up, gradually losing energy until it finally settles at the bottom. The Milky Way and Andromeda are going to do something similar, except the bowl is made of their combined gravitational field, and instead of a ball, you have two collections of hundreds of billions of stars. This back and forth process is what astronomers call a merger, and it's fundamentally different from a collision in the way we usually think about the word. When two cars collide, they crumple, they break apart, pieces fly everywhere. But galaxies don't work like that. They're not solid objects. They're more like clouds of stars held together by gravity, with enormous amounts of empty space between the individual stars. Let me give you a sense of just how much empty space we're talking about. The nearest star to our Sun is Proxima Centauri, about 4.2 light years away. That's roughly 25 trillion miles. If you shrunk the Sun down to the size of a grain of sand, about 1 millimeter across, then on that same scale, Proxima Centauri would be another grain of sand about 30 kilometers away. That's how sparse stars are, even within a galaxy. So when two galaxies merge, the stars themselves almost never actually collide with each other. The distances between them are just too vast. It's like taking two swarms of gnats and flying them through each other. Even though each swarm contains thousands of insects, the chances of any two gnats actually hitting each other is incredibly small, because there's so much empty space between them. But even though the stars don't physically collide, they still interact through gravity. Every star pulls on every other star. And when you have hundreds of billions of stars all pulling in different directions, the result is chaos. The orderly spiral structure gets disrupted. Stars get scattered into new orbits. Some stars get flung out of the galaxies entirely, ejected into the dark emptiness of intergalactic space. And the gas and dust between the stars, which is much more spread out and diffuse than the stars themselves, gets compressed, heated, and stirred up in ways that trigger enormous bursts of new star formation. This is what makes galaxy mergers so spectacular to study. They don't destroy galaxies in the sense of blowing them up or breaking them apart. Instead, they transform them. They take the orderly structures that existed before and scramble them into something completely new. And in the process, they create conditions for new generations of stars to be born. Now, let's talk about where we are right now, in the present day. Andromeda is still 2.5 million light-years away. That's so far that the light we see from it tonight left that galaxy when our ancestors were still primitive hominids living in Africa, before the genus Homo even existed. At its current speed, Andromeda is getting about 2,000 miles closer every minute. That sounds fast, but given the distances involved, it's going to be a very long time before anything dramatic happens. For the next few billion years, not much will change. Andromeda will continue to approach, getting very slightly brighter and larger in our night sky. But the change will be so gradual that no human lifetime would be long enough to notice it. You could observe Andromeda at the beginning of your life, and again at the end, using the best telescopes available, and you wouldn't be able to detect any difference. But things will start to get interesting in about 3.75 billion years. That's when Andromeda will be close enough that its gravitational influence on the Milky Way becomes significant. The two galaxies will start to distort each other, their shapes warping as the tidal forces between them grow stronger. Tidal forces are the same thing that causes ocean tides on Earth. The moon pulls on the Earth, but it pulls harder on the side of Earth that's closer to it, and less hard on the side that's farther away. This difference in gravitational pull stretches the Earth very slightly, and the oceans, being fluid, respond by bulging toward and away from the moon. That's what creates high tide. The same thing happens with galaxies, just on a much larger scale. As Andromeda gets closer, it pulls harder on the side of the Milky Way that faces it, and less hard on the far side. This stretches the Milky Way, distorting its shape. And the Milky Way does the same thing to Andromeda. Both galaxies start to develop tidal tails, long streams of stars pulled out from the main body of the galaxy by these tidal forces. If you could watch this process unfold in fast forward, sped up so that millions of years pass in seconds, you'd see the two galaxies approaching each other, their spiral arms beginning to distort and stretch, long filaments of stars being pulled out into space. The neat, orderly spiral structure that both galaxies have maintained for billions of years starts to come apart. About 3.85 billion years from now, the first close approach happens. The two galaxies don't hit head-on. Instead, they pass close by each other, maybe coming within about 100,000 light-years at their nearest point. As they pass, the gravitational interaction becomes intense. Stars that were peacefully orbiting in their home galaxy suddenly find themselves pulled in new directions. Some stars from the Milky Way get captured by Andromeda's gravity and start orbiting Andromeda instead. Some stars from Andromeda get captured by the Milky Way, and many stars get flung out into intergalactic space, no longer bound to either galaxy. The tidal tails grow longer and more pronounced. If you were watching from a safe distance outside both galaxies, you'd see these long, graceful arcs of stars stretching out behind each galaxy, like cosmic contrails. These tails can extend for hundreds of thousands of light years, and they're made up of millions of stars that have been torn away from their home galaxy. Now, what about the gas and dust? This is where things get really interesting. Unlike stars, which are separated by vast distances and rarely collide, gas clouds can and do collide. When two galaxies merge, their gas clouds slam into each other at hundreds of kilometers per second. This compresses the gas, heating it up and increasing its density. And when gas gets dense and compressed, it starts to collapse under its own gravity, forming new stars. This process, called a starburst, is one of the most spectacular phenomena in astronomy. During a starburst, a galaxy can form new stars at a rate hundreds or even thousands of times faster than normal. For a few 100 million years, the merging system lights up with the blue-white glow of massive young stars being born. These young, massive stars don't live long. The most massive ones burn through their fuel in just a few million years, then explode as supernovae. So a starburst phase is followed by a supernova phase, where the galaxy is lit up by frequent brilliant explosions as these young giants reach the end of their short lives. Each supernova enriches the surrounding gas with heavy elements that were created in the cores of these massive stars and flung into space by the explosion. This enriched gas will eventually form the next generation of stars that will have higher concentrations of elements like carbon, oxygen, silicon, and iron. Elements that are essential for planets and, ultimately, for life. After the first close passage, the two galaxies move apart again, but they don't escape. They're still bound together by gravity, and that gravity pulls them back toward each other. About 500 million years after the first passage, they swing back and pass through each other a second time. Then a third time. Each passage stirs up more gas, triggers more starbursts, and scatters more stars into new orbits. This dance continues for about 2 billion years. Each passage is a little different, a little less extreme than the one before, as the galaxies gradually lose energy and settle into a more stable configuration. Think of it like a bell that's been struck. It rings loudly at first, then the vibrations gradually dampen down until finally it's still. By about 6 billion years from now, the merger is essentially complete. The two galaxies have fully combined into a single new galaxy. The spiral structure is gone, replaced by a more elliptical shape. This new galaxy, which astronomers have already nicknamed Milkomeda, or sometimes Milkomeda, will be an elliptical galaxy, a smooth, football-shaped collection of stars with no spiral arms, no disk, and no ongoing star formation to speak of. Elliptical galaxies are the retirement homes of the galaxy world. They're made up mostly of old, red stars. There's very little gas left to form new stars, most of it having been used up during the starburst phase of the merger. The stars orbit in random directions rather than in the orderly circular orbits you see in a spiral galaxy. And without any young, bright blue stars being born, the galaxy takes on a reddish, yellowish hue. But Milkomeda will be enormous. It will contain all the stars from both the Milky Way and Andromeda, well over 1 trillion stars in total. It will be one of the largest galaxies in the local group, potentially even the largest depending on how the merger plays out and how much mass gets ejected in the process. Now, let's talk about what happens during all of this to our solar system, to our Sun and to Earth. Because that's probably what you're most curious about. If you're going to be living through a galaxy merger, assuming you could somehow survive that long, you'd want to know what to expect. The good news is that the solar system will almost certainly survive the merger intact. Remember what I said about how sparse stars are? The chances of another star passing close enough to our solar system to cause problems is extremely small. Even during the most chaotic phases of the merger, when stars are being scattered in all directions, the likelihood of a direct collision or even a close encounter is tiny. Astronomers have run computer simulations of the merger, modelling the motion of millions of stars to see what happens. In most simulations, the solar system passes through the merger without any close encounters. We might end up in a different part of the merged galaxy than where we started. Our orbit around the galactic centre might change, but the Sun and its family of planets remain intact. There is a small chance, maybe a few percent, that another star could pass close enough to disrupt the outer parts of the solar system. If a star came within a light year or so, it could disturb the Oort cloud, a vast sphere of icy objects that surrounds the solar system at a distance of about a light year from the Sun. This disruption could send some of those icy objects falling into the inner solar system, potentially increasing the rate of comet impacts on Earth. But even this is a relatively minor threat, and it's worth remembering that by the time the merger happens, Earth is going to have much bigger problems than the occasional comet. The Sun is slowly getting brighter. This isn't something you'd notice over a human lifetime, or even over thousands of years, but it's happening. The Sun's luminosity increases by about 10% every billion years. This is a natural part of the aging process for stars like the Sun. As they burn through their hydrogen fuel, they gradually heat up and produce more energy. In about 1 billion years, maybe a bit more, the sun will be bright enough that Earth's oceans start to evaporate. The increased heat will cause more water to evaporate into the atmosphere. Water vapor is a greenhouse gas, so this will trap more heat, causing even more evaporation in a runaway process. Within a few 100 million years, Earth's oceans will be gone, boiled away into space. The surface will become hot and dry, more like Venus than the Earth we know today. By about 3 billion years from now, well before the merger even begins, Earth will be completely uninhabitable. The surface temperature will be hundreds of degrees. Any water that once existed will be long gone. Life, at least life as we know it, will be impossible. So by the time Andromeda arrives, Earth will already be a dead world. The merger itself won't be what kills Earth. The sun's natural aging process will take care of that long before the galaxies collide. But let's imagine, just for the sake of argument, that Earth somehow remained habitable. Maybe humans, or whatever species we evolve into, figure out a way to keep the planet cool, some kind of massive planetary engineering project. What would the night sky look like during the merger? For the first few billion years, not much would change. Andromeda would very gradually get bigger and brighter, but the change would be so slow that you wouldn't notice it from year to year, or even from century to century. You'd need to compare observations separated by millions of years to see any difference. But as the first close approach nears, things would start to get dramatic. Andromeda would grow larger in the sky, eventually becoming visible as a distinct spiral structure even to the naked eye. Instead of a fuzzy smudge, you'd see spiral arms, dust lanes, bright star-forming regions. It would be spectacular, a second galaxy hanging in the sky, bright enough to cast shadows on a moonless night. As the galaxies pass through each other, the sky would become truly alien. You'd see stars from both galaxies mingled together. The familiar constellations would slowly distort and change as stars moved into new positions. New constellations would form from stars that were once part of Andromeda, now mixing with the Milky Way's stars. The starburst would be visible as well. Massive young stars, brilliant and blue, would light up regions of the sky that were previously dark. These stars would be scattered throughout the sky, not confined to the band of the Milky Way that we see today, and every few decades or centuries you'd see supernovae, stars exploding with such violence that they briefly outshine entire galaxies. For a few weeks, a supernova might be as bright as the full moon, visible even during the day. The tidal tails would be visible too, long arcs of stars stretching across the sky. Depending on where Earth ended up during the merger, you might see these tails as graceful bridges of light connecting different parts of the merged galaxy. It would be, without exaggeration, the most spectacular sky that any human-like observer could possibly witness. Every night would offer views that no telescope could capture from our present vantage point. The sky would be in constant slow motion, changing perceptibly over the course of decades and centuries as the merger progressed. Of course, there would also be increased hazards. The starburst would produce enormous amounts of radiation, not just visible light, but also ultraviolet radiation, X-rays, and gamma rays from the supernovae. If Earth were positioned near one of the star-forming regions, the radiation levels could be dangerous for life. The ozone layer might be stripped away, exposing the surface to harmful radiation. There's also the possibility of increased comet and asteroid impacts. The gravitational chaos of the merger could disturb the orbits of objects in the outer solar system, sending them careening into the inner system, where they might collide with planets. Earth has been hit by large asteroids before. The impact that killed the dinosaurs 66 million years ago was relatively small by cosmic standards, just a few kilometers across. But it was enough to cause mass extinctions and reshape the planet's climate for thousands of years. During a galaxy merger, such impacts might become more common. But again, these are relatively minor concerns compared to the fact that Earth will already be uninhabitable by the time any of this happens. The real question isn't whether Earth survives the merger, it's whether humanity, or whatever we evolve into, survives long enough to witness it. And that's actually an interesting question to think about. What would humanity look like in 4 billion years if we somehow survived that long? 4 billion years ago, Earth had just finished forming. Life was limited to simple single-celled organisms in the oceans. In the time between then and now, life evolved from those simple cells into everything we see today. Plants, animals, fungi, the entire diversity of life on Earth, including us. If you project forward another 4 billion years, assuming life and intelligence survive, the changes would be equally profound. We wouldn't be human anymore, not in any way we'd recognize. We'd be something else entirely, something shaped by billions of years of evolution, adaptation, and potentially technological enhancement. And if we're thinking about timescales this long, we also have to consider the possibility that humanity might leave Earth long before it becomes uninhabitable. We might spread to other planets, other star systems, other galaxies even. By the time the merger happens, our descendants might be scattered across thousands of worlds, living in habitats we can't even imagine. In that case, the merger wouldn't be a threat. It would be an opportunity, a chance to witness one of the most spectacular events in the universe, to study it up close, to learn from it. A civilization capable of surviving for 4 billion years would certainly have the technology to protect itself from any hazards the merger might pose. They could move planets if necessary, relocate entire populations to safer regions of space, even harness the energy released by the starburst for their own purposes. It's a beautiful thought, actually, that the distant descendants of humanity might gather to watch the merger, might build observatories and telescopes to study it, might send probes and spacecraft to explore the newly forming stars and planets. The merger that seems so distant and impersonal to us now might be a major cultural event for them, something they've been looking forward to for millions of years. But we're getting ahead of ourselves. Let's bring the focus back to the merger itself, because there's still one crucial element we haven't talked about yet: the supermassive black holes. Remember, both the Milky Way and Andromeda have supermassive black holes at their centres. The Milky Way's black hole, Sagittarius AI, weighs about 4 million solar masses. Andromeda's black hole is much larger, estimated at around 100 million solar masses, possibly more. When the galaxies merge, these two black holes will eventually merge as well, and that's going to be quite an event. In the early stages of the merger, the two black holes will be separated by hundreds of thousands of light years, each one sitting at the centre of its respective galaxy. But as the galaxies pass through each other and start to combine, the black holes will be pulled toward the centre of the merged system by gravity and by a process called dynamical friction. Dynamical friction is what happens when a massive object moves through a sea of less massive objects. The massive object gravitationally attracts the smaller objects, pulling them along in its wake. This creates a drag force that slows the massive object down. It's like trying to run through a crowded room. Even though you're not physically touching anyone, you have to slow down and navigate around people, and all those small interactions add up to slow you down. The black holes, being the most massive compact objects in their respective galaxies, experience this dynamical friction as they move through the clouds of stars and gas. It causes them to lose energy and spiral inward toward the centre of the merged galaxy. This process takes a long time, hundreds of millions of years, but eventually the two black holes will find each other. When they get close, within a few light years of each other, they'll be moving fast, orbiting each other at significant fractions of the speed of light. And they'll be emitting gravitational waves. Gravitational waves are ripples in the fabric of space-time itself, produced by accelerating masses. Einstein predicted their existence in 1916, and they were finally directly detected in 2015 by the LIGO experiment. That first detection was of two black holes, much smaller than galactic centre black holes, merging together. The gravitational waves from that event had travelled for over 1 billion years to reach Earth, and by the time they arrived, they were so faint that they could barely be detected even with the most sensitive instruments ever built. The merger of Sagittarius A and Andromeda's black hole will produce gravitational waves much stronger than anything LIGO has detected. For the last few years before the black holes merge, as they spiral closer and closer together, they'll be emitting gravitational waves powerful enough to be detected by civilizations anywhere in the local group. If humanity's descendants are still around, and if they have the technology to detect gravitational waves, they'll be able to watch the merger unfold not through telescopes, but through gravitational wave detectors. The final merger, when the two black holes actually collide and combine into a single black hole, will last just a few minutes. But in those few minutes, they'll release more energy in gravitational waves than all the stars in the observable universe emit in light during the same time period. It will be, briefly, the most powerful event. In the local group, the merged black hole will weigh about 104 million solar masses, the sum of the two original black holes, and it will sit at the centre of Milkomeda, anchoring the new galaxy just as the individual black holes anchored the Milky Way and Andromeda. Now, let's think about what Milkomeda will actually look like once the merger is complete. We've talked about the process, the gradual approach, the multiple passages, the starburst, the black hole merger, but what's the end result? What kind of galaxy emerges from all this chaos? As I mentioned earlier, Milkomeda will be an elliptical galaxy. But let's dig into what that really means and why mergers produce elliptical galaxies instead of spirals. Spiral galaxies like the Milky Way and Andromeda are what astronomers call disk galaxies. Most of their stars orbit in roughly the same plane, creating that characteristic flat disk shape. The stars move in orderly circular orbits around the galactic centre, all going in the same direction, like cars on a racetrack. This orderly motion is what allows spiral arms to form and persist over billions of years. But when two spiral galaxies merge, all that order gets disrupted. Stars from one galaxy pass through the other. Their orbits get bent and twisted by gravitational interactions with stars from the other galaxy. What was once orderly circular motion becomes chaotic and randomized. Stars end up moving in all different directions, some orbiting one way, some orbiting the other way, some moving in highly elongated elliptical orbits that take them far from the galactic centre and then back again. When you take billions of stars all moving in random directions and let gravity pull them together, you don't get a disk. You get a sphere, or more accurately an ellipsoid, a football shape. That's an elliptical galaxy. The stars are distributed in a smooth, roughly spherical or football-shaped cloud, with no spiral arms, no disk, and no preferred direction of motion. Elliptical galaxies are also generally much redder than spiral galaxies. This is because they contain mostly old stars. During the starburst phase of the merger, most of the gas gets used up to form stars. Once that gas is gone, there's nothing left to make new stars with. The massive young blue stars that form during the starburst live fast and die young, exploding as supernovae within a few tens of millions of years. After a few 100 million years, all those blue stars are gone, leaving behind only the longer-lived red and yellow stars. These old stars don't produce much light compared to the young blue giants, so elliptical galaxies, despite containing hundreds of billions or even trillions of stars, are actually somewhat dim compared to active spiral galaxies with ongoing star formation. They're the cosmic equivalent of retirement communities, quiet and sedate, their wild youth long behind them. Milkomeda will be a fairly large elliptical galaxy by any standard. It will span about 200,000 to 300,000 light-years across, significantly larger than either the Milky Way or Andromeda individually. But it won't be the largest elliptical galaxy in the universe. There are giant elliptical galaxies in the centres of large galaxy clusters that are several times larger, with masses measured in tens of trillions of solar masses. Those galaxies formed from the merger of dozens or even hundreds of smaller galaxies over billions of years. But in our local neighbourhood, In the local group, Milkomeda will be the dominant galaxy. The other galaxies in the local group are much smaller, and most of them will eventually be absorbed by Milkomeda over time. The two Magellanic Clouds currently orbiting the Milky Way will probably merge with Milkomeda at some point. So will the Triangulum Galaxy, the third largest member of the local group. Give it another few billion years beyond the Milky Way Andromeda merger, and most of the local group will have been incorporated into one giant elliptical galaxy. This is actually the fate of most galaxies in the universe. In regions where galaxies are close together, they eventually merge. Over cosmic time, small galaxies combine to form larger ones, and those larger ones merge to form even larger ones. It's a hierarchical process, building bigger structures from smaller pieces over billions of years. But there's a limit to how much merging can happen, and it has to do with the expansion of the universe. The universe is expanding, and that expansion is accelerating. This means that galaxies that are far apart are moving away from each other, carried along by the expansion of space itself. Eventually, they'll be so far apart that their mutual gravity can no longer pull them together, and they'll never merge. The local group is small enough and compact enough that its galaxies are gravitationally bound together. The expansion of the universe can't pull them apart. But galaxies and other groups, galaxies that are tens or hundreds of millions of light years away, are receding from us because of cosmic expansion. We'll never merge with them. In fact, as the expansion continues and accelerates, they'll eventually be moving away so fast that light from them can no longer reach us. They'll disappear beyond our cosmic horizon. So in the very distant future, trillions of years from now, the universe will be a lonely place. Each galaxy group will be isolated, surrounded by empty space that's expanding faster than light can cross it. Milkomeda will be alone, or nearly alone, with perhaps a few small dwarf galaxies for company. And there will be no way to tell that there were once billions of other galaxies out there, because they'll all be too far away to see. But that's a problem for the far, far future. Let's get back to Milkomeda and what life might be like in that galaxy. One thing that's interesting to think about is how the merger affects planets and the possibility of life. We've already established that Earth itself will be long dead by the time the merger happens, but there will be other planets, billions of them, scattered throughout both galaxies. What happens to them during the merger? For the most part, planets will be fine. Just like stars rarely collide during a galaxy merger, planets orbiting those stars will stay safely in their orbits. The gravitational interactions that scramble the orbits of stars are on such a large scale that they don't significantly affect individual planetary systems. The planets are held too tightly to their parent stars by gravity to be easily dislodged. There are a few scenarios where planets could be affected though. If a star passes very close to another star, within a light year or so, the gravitational interaction could potentially strip away planets in the outer parts of the system. A planet like Neptune, far from its star, might be more vulnerable than a planet like Earth, closer in. There's also the possibility that free-floating planets, planets that don't orbit any star, might be captured by other stars during the merger. Astronomers think there could be billions of these rogue planets wandering through the galaxy, either ejected from their original star systems or formed in isolation. During the chaos of a merger, some of these rogue planets might be captured by stars that didn't previously have planets, suddenly giving those stars a planetary system. But the more interesting question is what happens to life during a merger? Could life survive? Could it even thrive? The answer is complicated. On one hand, the merger creates hazards. The starburst produces intense radiation. Supernovae go off frequently, potentially close enough to sterilize nearby planets. The increased stellar density in some regions means more stars passing close by, potentially disrupting planetary systems or sending comets crashing into inner planets. On the other hand, the merger also creates opportunities. The starburst forms millions of new stars in a relatively short time. Many of those stars will have planetary systems. Within a few 100 million years, some of those planets could develop life. So while the merger might be hazardous for existing life, it also creates a vast number of new potential homes for life. There's also the fact that life is remarkably resilient. On Earth, life has survived multiple mass extinctions, including at least one event, the Late Heavy Bombardment about 4 billion years ago, where the entire surface was bombarded by asteroids and comets. Life found a way to survive, hiding in deep ocean vents or underground, waiting for conditions to improve. If life can survive that, it can probably survive a galaxy merger, especially if it has time to adapt and evolve. And remember, the merger plays out over billions of years. That's plenty of time for life to evolve, adapt, and potentially develop intelligence and technology. A technological civilization could see the merger coming, could predict when and where the hazards would be greatest, and could take steps to protect itself. They could move to safer star systems, build underground shelters to protect against radiation, or even leave the galaxy entirely if necessary. In fact, a galaxy merger might be exactly the kind of event that motivates civilizations to become spacefaring. If you know that your homeworld might become uninhabitable in a few million years due to increased radiation or other hazards, that's a powerful incentive to develop the technology to move to another planet or another star system. The merger could act as a selection pressure, favouring civilizations that are adaptable, forward-thinking, and capable of long-term planning. There's even a speculative but fascinating possibility that the merger could facilitate contact between civilizations from the two galaxies. Right now, if there are other intelligent civilizations in the Milky Way, they're separated from us by thousands of light years at minimum. Communication would take thousands of years for each message. Travelling between stars would take even longer with any plausible technology. But during the merger, as stars from both galaxies mix together, civilizations that were previously separated by millions of light years could suddenly find themselves relatively close neighbours. Of course, this assumes a lot. It assumes that intelligent life exists in both galaxies, that multiple civilizations arise around the same time, and that they have the technology and desire to make contact. Those are big assumptions. But if they're true, the merger could be a meeting of civilizations, not just a collision of stars. On a more fundamental level, the merger might actually improve conditions for life in some ways. In a typical spiral galaxy, star formation gradually declines over time as the available gas gets used up. Eventually, the galaxy would run out of gas, stop forming stars, and slowly fade as its existing stars age and die. But a merger stirs up the gas, triggers a new burst of star formation, and essentially resets the clock. It keeps the galaxy active and vibrant for billions of years longer than it would have been otherwise. And the mixing of gas from different parts of both galaxies means that new stars forming during and after the merger will have access to a well-mixed reservoir of elements. The heavy elements created in the cores of massive stars, scattered by supernova explosions, get mixed throughout the merging system. This could lead to the formation of planets with ideal compositions for life, with just the right mix of carbon, nitrogen, oxygen, phosphorus, iron, and other essential elements. So while a galaxy merger is certainly disruptive, it's not simply destructive, it's transformative. It creates new possibilities alongside the challenges, and on the timescales we're talking about, billions of years, life has plenty of time to adapt, evolve, and potentially take advantage of the new opportunities. Now let's zoom back out and think about the bigger picture. The merger of the Milky Way and Andromeda isn't just a local event. It's part of a much larger story about how the universe has evolved and continues to evolve. In the early universe, shortly after the Big Bang, there were no galaxies. There were just clouds of hydrogen and helium gas, distributed more or less uniformly throughout space. But those clouds weren't perfectly uniform. Some regions were slightly denser than others, and those denser regions had slightly stronger gravity, which pulled in more gas from the surrounding space, making them even denser. This created a feedback loop. denser regions grew denser, forming the first stars and the first galaxies. At first, these galaxies were small, just millions of stars instead of billions. But they grew over time, both by forming new stars from their gas and by merging with other small galaxies. This process, called hierarchical structure formation, built larger and larger galaxies over billions of years. The Milky Way is the product of countless mergers. Astronomers can see evidence of this in the structure of the galaxy and in the orbits of stars. There are streams of stars, remnants of small dwarf galaxies that were torn apart and absorbed by the Milky Way billions of years ago. There are clusters of old stars with unusual chemical compositions, suggesting they formed in a different galaxy and were later incorporated into the Milky Way. Andromeda has a similar history. It's been growing through mergers for its entire existence, and now it's the Milky Way's turn to participate in the process. But here's what's interesting. In the early universe, galaxy mergers were much more common than they are now. Galaxies were closer together, they were smaller and more numerous, and they merged frequently. The rate of galaxy mergers peaked about 10 billion years ago, when the universe was only a few billion years old. Since then, the merger rate has been declining because the universe has been expanding, pushing galaxies farther apart. Today, we're in a relatively quiet era. Galaxies in dense galaxy clusters still merge occasionally, but isolated galaxies like the Milky Way and Andromeda don't have many neighbours close enough to merge with. The merger of the Milky Way and Andromeda is one of the last major mergers that will happen in the local group. After Milkomeda forms, and after it absorbs the Triangulum galaxy and perhaps a few other small galaxies, that will be it. There won't be any more mergers in our region of space. Milkomeda will sit alone, slowly aging, slowly using up its remaining gas, slowly fading as its stars burn out and die. And eventually, trillions of years from now, even the stars themselves will be gone. The longest-lived stars, small red dwarfs that burn their fuel slowly and efficiently, can live for trillions of years. But even they will eventually run out of fuel and fade to cold, dark cinders. When that happens, Milkomeda will be a galaxy of dead stars, black holes, neutron stars, and white dwarfs, all slowly orbiting the central supermassive black hole in eternal darkness. That's the ultimate fate of all galaxies, at least as we understand it given the current state of physics. The universe will expand forever, carrying galaxies apart until they're isolated beyond each other's cosmic horizons. Each galaxy will use up its gas, stop forming stars, and fade into darkness. The stars will die, leaving behind compact remnants that slowly cool and fade. Eventually, even those remnants will decay, though this takes an unimaginably long time, far longer than the current age of the universe. It's a bleak picture, admittedly, but it's also so far in the future that it's almost meaningless. We're talking about timescales of trillions of years, thousands of times longer than the current age of the universe. Anything could happen in that time. Our understanding of physics could be completely wrong. New physical processes we haven't discovered yet could change the fate of the universe. It's hard to make predictions on those timescales with any confidence. For now, let's focus on what we can understand and predict with some confidence. The merger of the Milky Way and Andromeda will happen in about 4 billion years. It will take roughly 2 billion years to complete. The result will be a large elliptical galaxy containing over 1 trillion stars, and for any observers who happen to be around to witness it, it will be one of the most spectacular astronomical events imaginable. But there's another aspect of this merger that we haven't fully explored yet, and that's the role of dark matter. When astronomers talk about the mass of a galaxy, most of that mass isn't actually in stars. It's in dark matter, this mysterious substance that doesn't emit or absorb light, that doesn't interact with normal matter except through gravity. We can't see it directly, but we know it exists because of its gravitational effects on the things we can see. The Milky Way's dark matter halo extends far beyond the visible edge of the galaxy, out to maybe 600,000 or even 1 million light-years from the centre. Andromeda has a similar halo. These halos are what dominate the gravitational interaction during the merger. When we say the galaxies are pulling on each other, what we really mean is that their dark matter halos are pulling on each other. The visible parts of the galaxies, the stars and gas that we can actually see, are just small, relatively dense cores embedded in much larger halos of dark matter. It's like two icebergs colliding. The parts you see above the water are just the tips. The bulk of the mass is hidden below the surface. When the dark matter halos collide, they pass through each other just like the stars do. Dark matter particles don't collide or interact with each other, except through gravity, so the halos can interpenetrate completely. But as they do, their gravitational interaction slows them down. They lose energy, and eventually they merge into a single larger dark matter halo that surrounds Milkomeda. This dark matter halo will be enormous, extending perhaps 1 million light-years or more from the centre of Milkomeda, and it will contain most of the mass of the merged galaxy. Astronomers estimate that in a typical galaxy, about 85% to 90% of the total mass is dark matter. Only 10% to 15% is normal matter, the stuff that makes up stars, planets, and us. So when we talk about Milkomeda having a mass of several trillion solar masses, most of that mass is dark matter. The visible stars and gas, despite numbering in the trillions, are actually a minority of the total mass. We still don't know what dark matter is. It's one of the biggest unsolved mysteries in physics. We know it exists, we can measure its gravitational effects, but we don't know what particles it's made of or how to detect it directly. Dozens of experiments have searched for dark matter particles, but so far none have found anything conclusive. Understanding dark matter is crucial for understanding galaxy mergers because it's the dark matter that drives the dynamics of the merger. The stars and gas follow along, responding to the gravitational potential created by the dark matter halos. If we want to predict exactly how the merger will unfold, we need to understand how dark matter behaves. Fortunately, even though we don't know what dark matter is, we understand how it behaves gravitationally, and that's enough to make pretty good predictions about the merger. The simulations I mentioned earlier, the ones that model millions of stars to predict the outcome of the merger, also include dark matter. They treat it as a collection of particles that only interact gravitationally, and that seems to work well for making predictions. Now there's one more player in this story that we need to talk about, and that's the Triangulum galaxy. Triangulum is the third largest galaxy in the local group, after the Milky Way and Andromeda. It's a smaller spiral galaxy, containing maybe 40 billion stars, and it's located about 3 million light-years from us. Triangulum is also moving, and its motion is complex because it's being pulled by both the Milky Way and Andromeda. Some astronomers think Triangulum might already be gravitationally bound to Andromeda, essentially a large satellite galaxy. Others think it's an independent galaxy that will eventually be pulled into the merger. Either way, Triangulum will probably merge with the Milky Way and Andromeda at some point. It might merge during the same time frame as the main Milky Way-Andromeda collision, adding its stars to the chaos. Or it might happen later, after Milkomeda has already formed. The exact timing depends on Triangulum's precise motion, which is difficult to measure because it's so far away. If Triangulum does merge during the same time frame as the main event, it will add another layer of complexity to the already chaotic process. You'd have 3 galaxies all interacting with each other simultaneously, stars and gas being pulled in multiple directions at once. The resulting merged galaxy might be slightly larger and more massive than if it were just the Milky Way and Andromeda. But even without Triangulum, the merger is plenty complicated. We're talking about hundreds of billions of stars, each one following its own path through the gravitational field created by hundreds of billions of other stars, all moving and changing over billions of years. It's an almost impossibly complex problem to solve exactly. That's why astronomers rely on computer simulations. They can't calculate the motion of every single star exactly, but they can approximate the behaviour of the system by modelling millions of representative particles and letting the computer calculate how they evolve over time. These simulations have gotten increasingly sophisticated over the years as computers have gotten more powerful, and they've given us a pretty good picture of what to expect. but simulations have limitations. They make assumptions about things like the distribution of dark matter, the amount of gas in each galaxy, and how that gas behaves when it's compressed during the merger. Small changes in these assumptions can lead to different outcomes, so while we have a good general picture of what will happen, the details are still uncertain. For example, we know that the merger will produce a starburst, but we don't know exactly how intense it will be or how long it will last. We know that stars will be scattered into new orbits, but we can't predict exactly where any individual star, including our Sun, will end up. We know that the black holes will merge, but we don't know exactly how long it will take for them to spiral together once they're close. These uncertainties don't change the big picture. The merger will happen, it will produce an elliptical galaxy, and it will be spectacular. But the fine details remain somewhat fuzzy, and they'll probably stay that way until we can observe other galaxy mergers in better detail and refine our understanding of the physics involved. Actually, one of the best ways astronomers learn about galaxy mergers is by observing mergers that are happening right now in other parts of the universe. There are thousands of galaxy pairs in various stages of merging visible through powerful telescopes. Some are just starting to interact, their spiral structures just beginning to distort. Others are in the middle of the merger, with tidal tails stretching out and starbursts lighting up the collision zone. Still others are in the final stages, settling into their new elliptical shapes. By studying these mergers at different stages, astronomers can piece together the full timeline of what happens during a merger. It's like watching a time-lapse video, except instead of one object changing over time, you're looking at many different objects, each one frozen at a different moment in the process, and inferring the timeline from that. One famous example is the antennae galaxies, a pair of spiral galaxies about 45 million light-years away that are currently in the midst of a merger. They get their name from the long tidal tails that extend out from the merging galaxies, looking somewhat like the antennae of an insect. These tails are made of millions of stars pulled out from the main bodies of the galaxies by tidal forces. The collision zone between the two galaxies is lit up with bright young star clusters, evidence of the intense starburst triggered by the merger. The antennae galaxies are often used as a preview of what will happen when the Milky Way and Andromeda merge. The two mergers aren't exactly the same, of course. The antennae galaxies are somewhat smaller than the Milky Way and Andromeda, and the details of their collision are different. But the basic physics is the same, and studying the antennae gives us valuable insights into what to expect in our own backyard. Another famous merging system is the mice galaxies, named for their long tails that look like the tails of mice. And then there's ARP-87, a pair of galaxies connected by a bridge of stars stretching between them. Each of these systems shows a different aspect of the merger process, a different snapshot of the billions of years of evolution that transforms two spiral galaxies into one elliptical. These observations have taught us a lot. For example, we've learned that the starburst phase is often concentrated in specific regions where the gas clouds from the two galaxies collide most directly. We've learned that tidal tails can extend for hundreds of thousands of light years, containing millions of stars in long, graceful arcs. We've learned that some stars get ejected from the merging system entirely, becoming intergalactic wanderers with no galaxy to call home. We've also learned that galaxy mergers are not rare events. They happen all the time throughout the universe. In the early universe, when galaxies were smaller and closer together, mergers were even more common. It's one of the primary ways that galaxies grow and evolve. In fact, almost every large galaxy we see today, including the Milky Way and Andromeda, is the product of multiple mergers that happened over billions of years. This raises an interesting philosophical point. We tend to think of galaxies as distinct, separate entities, each with its own identity. We talk about the Milky Way as if it's a thing, a single coherent object. But in reality, galaxies are temporary assemblages of stars, gas, and dark matter that form, evolve, merge with other galaxies, and eventually disperse or fade away. They're not eternal. They're not even particularly stable over cosmic timescales. They're just structures that happen to exist for a while before circumstances change and they transform into something else. The same is true of everything in the universe, really. Stars form, live for a while and die. Planets form, evolve, and eventually either get destroyed or become lifeless rocks orbiting dead stars. Even the atoms in our bodies are temporary. They were created in stars billions of years ago. They happen to be part of us now, but eventually they'll be part of something else, scattered into space when the sun dies, perhaps incorporated into new stars and planets billions of years from now. Nothing is permanent. Everything changes. The merger of the Milky Way and Andromeda is just one example of this universal truth, playing out on a grand scale over billions of years. But within that impermanence, there's also continuity. The atoms that make up the Milky Way and Andromeda won't be destroyed during the merger. They'll just be rearranged. The stars will still exist, just in different orbits, in a different configuration. The gas will still exist, some of it transformed into new stars, some of it remaining as gas in the new galaxy. Even the dark matter halos will still exist, merged into a single larger halo. So Milkomeda isn't the destruction of the Milky Way and Andromeda. It's their transformation, their evolution into a new form. The information about where those galaxies came from, their history of previous mergers, the generations of stars that lived and died in them, all of that is preserved in some sense in the structure and composition of Milkomeda. Astronomers call this galactic archaeology. By studying the stars in a galaxy, measuring their ages, their compositions, their motions, we can reconstruct the history of that galaxy. We can identify which stars came from which previous galaxy. We can figure out when mergers happened, how big the merging galaxies were, what the conditions were like when different generations of stars formed. It's like being a detective, piecing together clues to solve a mystery that happened billions of years ago. And it's one of the most exciting areas of modern astronomy, because it allows us to understand not just what galaxies look like now, but how they got that way. The whole chain of events stretching back to the early universe that led to the galaxies we see today. In the case of Milkomeda, future astronomers living billions of years from now will be able to look at the stars in their galaxy and piece together the story of the merger. They'll be able to identify which stars came from the Milky Way and which came from Andromeda based on their orbits and compositions. They'll be able to date the starburst phase by looking at the ages of stars born during that period. They'll be able to see the streams and shells of stars left over from the chaotic mixing of the two galaxies, and they'll know that their galaxy is the product of a merger, that it wasn't always this way, that billions of years ago there were two separate galaxies that came together to create the galaxy they call home. That story will be written in the stars themselves, waiting to be read by anyone with the knowledge and tools to decipher it. There's something profound about that idea, that the history of the universe is preserved in the structures we see around us. Every galaxy tells a story. Every star is a clue to past events. The universe doesn't forget its history. It records it in the distribution of matter, in the motion of stars, in the chemical composition of gas clouds. We just have to learn how to read the records. Now, let's talk about some of the more speculative aspects of the merger. Things that might happen but that we're less certain about. One possibility is that the merger could trigger activity in the supermassive black holes before they actually merge with each other. Remember, both galaxies have these enormous black holes at their centres. Most of the time, these black holes are relatively quiet. They're not actively consuming large amounts of matter, so they're not producing much radiation. But during a merger, gas gets funneled toward the centre of the galaxy by the gravitational chaos. Some of that gas could fall into the black holes, and when gas falls into a black hole, it heats up and emits enormous amounts of radiation. This is what creates what astronomers call an active galactic nucleus, or AGN. An AGN is one of the brightest objects in the universe. A supermassive black hole actively feeding on gas can outshine all the stars in its host galaxy combined. It produces not just visible light, but also intense X-rays, ultraviolet radiation, and in some cases powerful jets of particles shooting out at nearly the speed of light. If the merger triggers AGN activity in one or both of the black holes, Milkomeda would light up like a beacon visible across hundreds of millions of light years. This would last for a relatively brief period, maybe a few million to a few tens of millions of years, before the available gas near the black holes gets consumed and they quiet down again. During that time, the radiation from the AGN could have significant effects on the galaxy. It could heat up the surrounding gas, preventing it from collapsing to form new stars. It could even drive powerful winds that push gas out of the galaxy entirely. Some astronomers think that AGN feedback, as this process is called, is one of the reasons elliptical galaxies stop forming stars. The black hole heats up or expels the gas, leaving nothing for future star formation. For any planets in the galaxy during this period, an active AGN would be both spectacular and potentially hazardous. The night sky would be dominated by the brilliant glow of the galactic core, bright enough to cast shadows even if you were thousands of light years away. But the radiation, especially the X-rays and ultraviolet, could be dangerous for life, particularly if your planet happened to be relatively close to the galactic centre. Another speculative but interesting possibility is the formation of intermediate mass, black holes during the merger. We know that supermassive black holes exist at the centres of galaxies, and we know that stellar mass black holes exist as the remnants of massive stars. But there's a gap in between. We haven't found many black holes with masses between about 100 solar masses and 1 million solar masses. During a merger, the dense environment in the star-forming regions could potentially create conditions for intermediate mass black holes to form. If a very dense star cluster forms, with thousands of stars packed into a small region, those stars could collide and merge, building up more and more massive stars. If this process continues, you might end up with a star so massive that it collapses directly into a black hole, potentially an intermediate mass black hole. These objects, if they exist, would be fascinating to study. They'd bridge the gap between stellar mass and supermassive black holes, and they might help us understand how supermassive black holes formed in the first place. Did they grow from stellar mass black holes, gradually consuming more and more matter? Or did they form directly from the collapse of massive gas clouds in the early universe? Intermediate mass black holes could provide clues to answering these questions. There's also the question of what happens to globular clusters during the merger. Globular clusters are dense spherical collections of old stars that orbit in the halos of galaxies. The Milky Way has about 150 to 200 globular clusters, each one containing hundreds of thousands to millions of stars packed into a region just a few dozen light years across. Andromeda has even more, maybe 500 or more globular clusters. During the merger, these globular clusters will be thrown into new orbits. Some might be torn apart by tidal forces if they pass too close to the galactic centre or to each other. Others might survive intact, becoming globular clusters of Milkomeda. And there's even a possibility that new globular clusters could form during the starburst phase, born in the dense star-forming regions created by the collision of gas clouds. Globular clusters are interesting because they're some of the oldest objects in galaxies. Many globular clusters in the Milky Way are over 12 billion years old, nearly as old as the universe itself. They're like time capsules, preserving information about the conditions in the early universe when they formed. If we can identify which globular clusters in Milkomeda came from the Milky Way and which came from Andromeda, we can learn about the early histories of both galaxies. There's also the question of heavy element enrichment. I mentioned earlier that supernovae create heavy elements and scatter them into space. These elements then get incorporated into the next generation of stars and planets. This is how the universe gradually becomes enriched, with elements heavier than hydrogen and helium. In the early universe, shortly after the Big Bang, there were only hydrogen and helium, with trace amounts of lithium. The first stars formed from this primordial gas, and when those stars died and exploded as supernova, they created the first heavy elements. Those elements mixed with the remaining gas, and the next generation of stars had slightly more heavy elements. This process has been continuing for billions of years, gradually enriching the gas with more and more heavy elements. The Sun, for example, is a relatively young star by cosmic standards, only about 4.6 billion years old. It formed from gas that had already been enriched by many previous generations of stars, which is why it contains a significant amount of heavy elements. About 2% of the Sun's mass is elements heavier than helium. That might not sound like much, but it's enough to form rocky planets like Earth, which are made almost entirely of heavy elements like iron, silicon, and oxygen. During a galaxy merger, the mixing of gas from different parts of both galaxies can create a more uniform distribution of heavy elements. Gas from the outer parts of the galaxies, which is less enriched, mixes with gas from the inner parts, which has been more heavily enriched by successive generations of stars. The result is that the next generation of stars forms from gas with a more homogeneous composition. This could have implications for the types of planets that form. If the gas is well mixed and has a good supply of heavy elements, you might get more rocky planets like Earth, planets that could potentially support life. On the other hand, if some regions have less enrichment, the planets forming there might be more gas-dominated like Jupiter and Saturn, with only small rocky cores. Of course, this is all highly speculative. We're still learning about planet formation, and there's a lot we don't understand about how the composition of the gas affects the types of planets that form. But it's an interesting area of research, and galaxy mergers provide a natural laboratory for studying these questions. Another aspect worth considering is the role of magnetic fields during the merger. Galaxies have magnetic fields threading through them, generated by the motion of charged particles in the gas, and by processes happening in stars. These magnetic fields are relatively weak by everyday standards, but they can have important effects on the behavior of gas, especially the diffuse gas between the stars. When the gas clouds from two galaxies collide during a merger, the magnetic fields get compressed and amplified. This can affect how the gas collapses to form stars. Magnetic fields can provide pressure that partially supports the gas against gravity, potentially slowing down or regulating the rate of star formation. They can also affect the way gas flows, channeling it along field lines and creating structures that wouldn't form otherwise. We're still working to understand the full role of magnetic fields in galaxy evolution and in galaxy mergers specifically. It's a challenging problem because magnetic fields are difficult to observe directly, and they interact with gas in complex ways that are hard to model. But as our computational capabilities improve and our observations become more detailed, we're gradually piecing together a better picture. There's also the question of cosmic rays. Cosmic rays are high-energy particles, mostly protons, that zoom through space at nearly the speed of light. They're created by supernovae, by active galactic nuclei, and by other energetic processes. Galaxies are filled with these cosmic rays, and they carry a surprising amount of energy, comparable in some cases to the energy in the galaxy's magnetic field or the kinetic energy of the gas. During a merger, the increased rate of supernovae would produce more cosmic rays. These cosmic rays could have various effects. They could provide additional pressure supporting the gas, affecting how it collapses to form stars. They could heat the gas through collisions with gas particles. They could even affect the chemistry of the gas, breaking apart molecules or ionizing atoms. For any life in the galaxy during the merger, cosmic rays could be an increased hazard. Earth is partially protected from cosmic rays by its magnetic field and atmosphere, which deflect or absorb most of them. But on a planet without these protections, or on a planet orbiting a star in a particularly cosmic ray-rich region of the galaxy, the radiation dose could be significantly higher. This might not be enough to prevent life altogether, but it could create additional evolutionary pressure, favouring organisms that are more resistant to radiation damage. Now, let's think about the really long-term consequences of the merger. Not just billions of years, but tens or even hundreds of billions of years into the future. After Milkomeda forms and settles into its new elliptical configuration, it will gradually use up its remaining gas through star formation. This process will take a long time because elliptical galaxies form stars much more slowly than spiral galaxies. But eventually the gas will run out, no more new stars will be born, and the galaxy will begin a slow fade into darkness as its existing stars age and die. The most massive stars will die first, living only a few million years before exploding as supernovae. Medium-mass stars like the Sun will last longer, about 10 billion years. Smaller stars, red dwarfs with masses less than half that of the Sun, can live for trillions of years, far longer than the current age of the universe. So even after star formation stops in Milkomeda, the galaxy will remain bright for a very long time, lit by the vast numbers of long-lived small stars, but very gradually, over tens and eventually hundreds of billions of years, even these long-lived stars will die, winking out one by one. When a star like the Sun dies, it sheds its outer layers and leaves behind a white dwarf, a dense, hot core, about the size of Earth. White dwarfs don't produce energy through fusion. They just slowly radiate away their stored heat, gradually cooling and fading over billions of years. Eventually, they cool enough that they stop emitting visible light, becoming what astronomers call black dwarfs. Though it takes so long for this to happen that there probably aren't any black dwarfs in the universe yet. The universe simply hasn't been around long enough for even the oldest white dwarfs to cool completely. More massive stars end their lives as neutron stars or black holes. These compact remnants are essentially eternal. A neutron star is a ball of neutrons about the size of a city, but with the mass of a star. It's so dense that a teaspoon of neutron star material would weigh about 1 billion tons. Black holes, of course, are even more extreme, regions of space-time where gravity is so strong that not even light can escape. So the final state of Milkomeda, hundreds of billions of years from now, will be a dark galaxy filled with stellar remnants. White dwarfs gradually cooling to black dwarfs, neutron stars spinning in the darkness, and black holes of various sizes scattered throughout. The supermassive black hole at the centre will still be there, possibly having grown even larger by consuming stars and gas that wander too close. At this point, Milkomeda will be essentially invisible. It will produce almost no light, just the faint infrared glow from cooling white dwarfs, and perhaps occasional flashes when two remnants collide, or when an unlucky star gets torn apart by the central black hole. From the outside, it would be almost undetectable, a vast concentration of mass lurking in the darkness. But even this isn't the end of the story. On even longer timescales, measured in trillions upon trillions of years, the stellar remnants will gradually fall toward the centre of the galaxy. This happens through a process called gravitational radiation. Any object moving through a gravitational field emits very faint gravitational waves, and those waves carry away energy. The object loses energy and spirals inward, very slowly. For stellar remnants orbiting in a galaxy, this process takes an almost unimaginably long time, something like 10 plus 20 years or longer. But given enough time, all the remnants would spiral into the central black hole, which would gradually consume the entire galaxy, growing to an enormous size in the process. Eventually you'd be left with just a single supermassive black hole, weighing trillions of solar masses, sitting alone in the darkness. And even that black hole would eventually evaporate through a process called Hawking radiation, though this takes even longer, perhaps 10-100 years or more. These timescales are so long that they're almost meaningless to us. They're longer than the current age of the universe by factors of billions or more. Our brains simply aren't equipped to comprehend timescales like this in any intuitive way. But they're worth thinking about because they remind us of the ultimate fate of everything in the universe. Nothing lasts forever, not even galaxies, not even black holes. But let's come back to more immediate timescales, things that might actually be relevant to us or our descendants. The merger of the Milky Way and Andromeda, beginning in about 4 billion years, is something that could conceivably be witnessed by intelligent observers, assuming that intelligence and technological civilization survive that long. And that raises an interesting question. What would it be like, from a cultural and philosophical perspective, to live through a galaxy merger? How would it affect a civilization's worldview, their sense of their place in the universe? For most of human history, the night sky has been seen as eternal and unchanging. The stars appear in the same positions year after year, century after century. The constellations that ancient civilizations knew are essentially the same ones we see today. This apparent permanence of the heavens has shaped many cultures, philosophies, and religions. The sky is often seen as a realm of perfection and unchanging order, in contrast to the messy, chaotic world of Earth. But a civilization witnessing a galaxy merger would know, in a visceral way, that nothing in the universe is permanent. They would watch the sky change over generations, would see new stars being born and old stars dying, would see the familiar patterns of constellations slowly distort and change as stars move into new positions. The sky itself would be proof that everything changes, that even the largest structures in the universe are temporary. This might profoundly affect their worldview. It might make them more aware of the passage of time, more conscious of their place in a vast, evolving cosmos. It might inspire a sense of urgency, a desire to make the most of their existence because nothing lasts forever. Or it might inspire a sense of connection to the cosmos, a feeling that they're part of a grand story unfolding over billions of years. Of course, this assumes that such a civilization would even think about these questions the way we do. A civilization that survives for billions of years would be so different from us that we probably couldn't even recognize them as our descendants. They might not even be biological. They could be artificial intelligences, or they could be some hybrid of biological and machine, or they could be something we can't even imagine with our current limited perspective. But whatever form they take, they would have an extraordinary view. They would be living through one of the universe's grandest transformations, watching billions of years of cosmic evolution unfold before their eyes, or their senses, or whatever they use to observe the universe. There's another question worth considering, and that's whether advanced civilizations might try to influence or control the merger in some way. This might sound like science fiction, but it's worth thinking about. If a civilization survives for billions of years and develops technology far beyond anything we can currently imagine, they might acquire the ability to move stars, or even to manipulate the structure of galaxies. This idea is sometimes called stellar engineering or galactic engineering. The basic concept is that with enough energy and the right technology, you could potentially move stars by surrounding them with structures that capture their light and convert it into thrust. Over very long timescales, you could relocate stars to different parts of the galaxy, or even move them out of the galaxy entirely. Why would you want to do this? Well, if you're a civilization spread across many star systems, and you know a galaxy merger is coming, you might want to move your stars to safer regions, away from areas where the starburst will be most intense, or where stellar encounters will be most likely. You could essentially custom design your region of the galaxy to be as safe and stable as possible. Or you might want to do the opposite. You might deliberately arrange stars in certain patterns, creating structures that would be recognizable to other civilizations as artificial. This could be a way of leaving a lasting mark on the universe, creating something that would persist for billions of years. Some scientists have speculated that we should look for such structures when we search for advanced alien civilizations. If they exist and have the capability, they might rearrange their local stellar neighborhood in ways that couldn't happen naturally. Of course, all of this is highly speculative. We have no idea whether such technology is even possible, let alone whether any civilization would choose to use it this way. But it's interesting to think about. The merger of the Milky Way and Andromeda isn't just an event that happens to us. It's an event that a sufficiently advanced civilization might be able to influence, shape, or even control to some degree. There's also the question of what we, as a civilization right now, should think about the merger. It's so far in the future that it might seem irrelevant to our current concerns. We have much more immediate problems to deal with: climate change, resource depletion, political conflicts, the various challenges of living on a single planet with limited resources. But in another sense, thinking about events like the merger puts our current problems in perspective. It reminds us that we're part of something much larger and longer lasting than our individual lives, or even than the entire span of human civilization so far. We're part of a galaxy, which is itself part of a larger cosmic structure, all of it evolving and changing over timescales that dwarf human history. This perspective can be humbling, but it can also be inspiring. It reminds us that the problems we face, as difficult as they might seem, are temporary challenges in the grand scheme of things. It reminds us that there's a future stretching out ahead of us, billions of years of potential for life, intelligence, and consciousness to exist and experience the universe. And it reminds us that we have a choice about what kind of future we create. The merger is inevitable, at least in the absence of any intervention by advanced civilizations, but how we respond to it, assuming our descendants are around to witness it, is up to us. We can prepare, we can adapt, we can potentially even influence the outcome in ways we can't yet imagine. But first we have to survive long enough to get there, and that means solving the problems we face now, on Earth in the present day. It means learning to live sustainably on our home planet. It means developing the technology to spread beyond Earth to other planets, and eventually other star systems. It means creating a civilization that can think and plan on very long timescales, not just years or decades, but centuries, millennia, and beyond. This is one of the great challenges facing humanity. We've evolved to think in terms of our individual lifespans, maybe a few generations at most, but the universe operates on much longer timescales. To truly thrive in the cosmos, we need to develop the ability to think on those timescales, to plan for futures that extend far beyond our own lives. The merger of the Milky Way and Andromeda is a reminder of this. It's a predictable event, something we can see coming billions of years in advance. If we survive long enough, if we develop the technology and the wisdom to navigate the challenges ahead, our descendants might be there to witness it. They might even play a role in shaping how it unfolds. Now let's think about one more aspect of this story, and that's what it tells us about the nature of galaxies and the universe as a whole. We tend to think of galaxies as fundamental units, building blocks of the universe, and in a sense they are. The universe is organised hierarchically. Planets orbit stars, stars are grouped into galaxies, galaxies are grouped into clusters, clusters are grouped into superclusters. At each level of this hierarchy, the structures are held together by gravity, constantly evolving and changing. But galaxies aren't fundamental in the sense of being eternal or unchanging. They're dynamic systems that form, grow, merge, and eventually fade. The galaxy we live in now, the Milky Way, is not the same galaxy that existed 10 billion years ago. It's grown through mergers with other galaxies. It's formed new generations of stars. The gas has been enriched with heavy elements. The structure has evolved. And the galaxy that exists 10 billion years from now, Milkomeda, will be different again. It will be larger, more massive, with a different structure and a different history of star formation. But in a sense, it will still be the same galaxy. The matter that makes up the Milky Way now will still exist. It will just be rearranged, transformed, incorporated into a new structure. This is what the universe does. It takes matter and energy and constantly rearranges them into new forms. Stars form from gas clouds, live for a while, and then return their matter to space, enriched with new elements. Planets form, evolve, and eventually either get destroyed or become lifeless remnants. Galaxies form, grow through mergers, and eventually fade. Black holes form, grow, and eventually evaporate. Nothing is permanent. Everything is in flux. The universe is a vast, ongoing process of transformation, matter, organising itself into increasingly complex structures for a while, then disassembling and reorganising in new ways. And yet, Within this constant change, there's a kind of continuity. The laws of physics remain the same. The fundamental particles that make up matter don't change. The overall structure of the universe, the large-scale distribution of galaxies and galaxy clusters, evolves in predictable ways according to those laws. This tension between change and continuity is one of the fundamental features of the universe. Things change, but they change according to rules. The merger of the Milky Way and Andromeda is an example of this. It's a dramatic transformation, billions of stars being scattered into new orbits, gas being compressed to form new stars, black holes merging together. But it all happens according to the laws of gravity and the other physical laws that govern the universe. We can predict how the merger will unfold because we understand those laws. We can simulate it on computers. We can observe other galaxy mergers happening elsewhere in the universe and see that they follow the same patterns. There's order in the chaos, predictability in the transformation. This is what makes science possible. If the universe were truly random, if things just happened without following any rules, we couldn't make predictions. We couldn't understand anything. But the universe does follow rules, and those rules allow us to understand not just what is, but what will be. We can look at the present state of the Milky Way and Andromeda, measure their positions and velocities, and predict that they will merge in about 4 billion years. We can describe what that merger will look like, even though it hasn't happened yet. This predictive power is one of the great triumphs of science. It shows that we're not just passive observers of the universe. We can understand it, we can predict it, and potentially, with enough knowledge and technology, we can even influence it, though that's something for future generations to determine. So what's the takeaway from all of this? What should we learn from thinking about the merger of the Milky Way and Andromeda? First, it reminds us of the scale of the universe, both in space and in time. The distances between galaxies are vast beyond human comprehension. The timescales on which they evolve are longer than we can intuitively grasp. This can be humbling, but it can also be inspiring. We're part of something much larger than ourselves. Second, it reminds us that nothing is permanent. Even galaxies, these enormous structures containing hundreds of billions of stars, are temporary. They form, they evolve, they merge, they fade. This is true of everything in the universe, from the smallest particles to the largest structures. Change is the only constant. Third, it shows us the power of science and human understanding. We can predict an event that won't happen for 4 billion years. We can describe what it will look like, how it will unfold, what the result will be. This is possible because we've learned to understand the laws that govern the universe, and we've developed the tools, both mathematical and observational, to apply those laws to make predictions. Fourth, it reminds us of the resilience of matter and structure. Even though galaxies can merge and transform dramatically, the underlying matter isn't destroyed, it's just rearranged. Stars survive the merger, planets survive, even life could potentially survive if it's clever and adaptable enough. Transformation isn't the same as destruction. And finally, it gives us a glimpse of what our distant future might hold. If humanity or its descendants survive for billions of years, they will witness events that we can only imagine. They will see the night sky transform. They will live through one of the universe's grandest spectacles, and they will have to adapt, evolve, and potentially move to other star systems to ensure their survival. The merger of the Milky Way and Andromeda is a long way off. By the time it happens, Earth will be uninhabitable, the Sun will be nearing the end of its life, and humanity, if it still exists, will be unrecognisably different. But the merger will happen, following the inexorable pull of gravity, unfolding over billions of years according to the laws of physics. It's a reminder that the universe has a future, a long future, stretching out ahead of us. And while we can't know all the details of what that future will hold, we can make predictions based on our understanding of how the universe works. The merger is one of those predictions, a future event we can see coming from billions of years away, And maybe, just maybe, someone will be there to witness it when it finally arrives. Someone or something descended from us, or descended from some other form of life that arises in the billions of years between now and then. They'll look up at their sky, at the great swirl of stars from two galaxies mingling together, at the bright young stars being born in the collision zones, at the brilliant core where the two supermassive black holes are slowly spiralling together. And they'll know they're witnessing something rare and spectacular, one of the great transformations of the cosmos. The final hour of the collision won't really be final at all. It will be a beginning, the birth of a new galaxy, a new structure that will persist for billions of years before it too eventually fades. That's the nature of the universe. Endings are beginnings. Destruction is transformation. And change, however dramatic, is just part of the ongoing story of matter organising itself into ever more complex forms, acting out the grand drama of cosmic evolution across billions of years. The merger is coming. The countdown has already begun, and in 4 billion years, give or take a few hundred million, when Andromeda finally arrives, it will be one of the most spectacular shows the universe has to offer. The night sky will never be the same again. Thanks for staying with me through this journey across billions of years and millions of light years. We've covered a lot of ground tonight, from the basic structure of the Milky Way and Andromeda, through the mechanics of how galaxy mergers actually work, to the specific timeline of what will happen when these two giants finally meet. We've talked about tidal forces and starbursts, about supermassive black holes spiralling together, about what the night sky might look like during the merger. We've considered what happens to Earth, to our Sun, to life itself during this grand cosmic transformation. And we've thought about the very long-term future, looking ahead not just billions, but trillions of years to see what ultimately becomes of Milkomeda. But beyond all the specific details and predictions, there's a larger message here that's worth emphasizing. The universe is not static. It's not a fixed stage on which events play out. It's a dynamic, evolving system where everything is constantly changing, from the smallest scales to the largest. The atoms in your body were created in stars that lived and died billions of years ago. Those stars were part of galaxies that formed from gas clouds in the early universe. Those galaxies merged with other galaxies, including the ancestors of the Milky Way. And now the Milky Way itself is on a collision course with Andromeda, beginning a transformation that will create something new. You're literally made of stardust, and the galaxy you live in is itself the product of countless mergers and transformations over billions of years. And the process continues. The merger with Andromeda is just the next chapter in an ongoing story that stretches back to the beginning of the universe and forward to its ultimate fate. This perspective, sometimes called the cosmic perspective, can be overwhelming. It makes our individual lives seem vanishingly small and brief. We live for decades in a universe that exists for billions of years. We occupy a tiny planet in a galaxy containing hundreds of billions of stars, and that galaxy is just one of hundreds of billions of galaxies in the observable universe. But I think this perspective can also be empowering. Yes, we're small. Yes, we're brief. But we're also part of something magnificent. We're conscious matter that has organised itself in such a way that it can observe and understand the universe it's part of. We're stardust that has learned to think, to wonder, to ask questions about where we came from and where we're going. And we're not just passive observers. We have the ability to act, to make choices, to shape the future, at least on some scales. We can't prevent the merger of the Milky Way and Andromeda. That's beyond our capability, probably forever. But we can choose how we respond to the challenges we face on shorter timescales. We can choose whether to survive long enough to witness the merger. We can choose what kind of civilization we want to be. The merger reminds us that we're living in a universe that has a past, a present, and a future. The past stretches back 13.8 billion years to the Big Bang. The present is this moment right now, where we find ourselves on a small planet orbiting an ordinary star in an ordinary spiral galaxy, and the future stretches forward, billions of years, to the merger and beyond. What we do now in this present moment echoes into that future. The choices we make, the things we build, the knowledge we accumulate, all of it becomes part of the ongoing story. If humanity survives, if we spread to other star systems, if we persist for billions of years, it will be because we made the right choices now, in these crucial early centuries of our technological civilization. And even if we don't survive, even if humanity goes extinct long before the merger happens, the universe will continue. Other forms of life might arise, other civilizations might develop. The merger will still happen, and it will still be spectacular, regardless of whether anyone is watching. But I like to think we will survive. I like to think that our descendants, whatever form they take, will be there to witness the merger. They'll have had billions of years to prepare to spread across the galaxy, to develop technologies we can barely imagine. They'll be ready for the transformation. And when the first close passage happens, when Andromeda swings by, and the tidal forces start to distort both galaxies, they'll gather to watch. They'll point their telescopes and sensors and whatever other instruments they've developed at the sky. They'll study the starburst regions, the tidal tails, the merging black holes. They'll add to the scientific knowledge that we started accumulating, centuries and millennia of observations and theories and predictions. And maybe they'll think about us, their ancient ancestors who first predicted this merger, who first understood what was coming. Maybe they'll remember that we were the ones who figured out that galaxies collide, who discovered Andromeda's blue shift, who ran the first computer simulations of the merger. Maybe we'll be remembered as the generation that first looked up at the night sky and truly understood what we were seeing. Or maybe not. Maybe billions of years is too long for any memory to persist, even cultural memory. Maybe by then we'll be so changed, so different from what we are now, that the connection between us and them will be too tenuous to recognize. Maybe they won't think of themselves as our descendants at all, but as something entirely new. But either way, the knowledge will persist. The understanding that galaxies merge, that the universe evolves, that nothing is permanent, that change is the fundamental nature of reality. These insights, these hard-won pieces of understanding about how the cosmos works, they'll still be there, built into the foundation of whatever civilization exists billions of years from now. That's the legacy of science. It's not about any individual scientist or any particular discovery. It's about the accumulation of knowledge over time, each generation building on what came before, gradually constructing a more complete and accurate picture of the universe we live in. The merger of the Milky Way and Andromeda is just one piece of that picture, but it's an important piece because it reminds us that even the largest structures in the universe are subject to change, that nothing is immune to the passage of time and the pull of gravity. So as we come to the end of this exploration, take a moment to think about what it means. We live in a universe that's 13.8 billion years old. We live in a galaxy that's been growing through mergers for most of that time. We live on a planet that's 4.6 billion years old, orbiting a star that will last for several billion more years before it dies. And in about 4 billion years, our galaxy will merge with Andromeda, creating something new, something that has never existed before. Milkomeda will be born from the collision of the Milky Way and Andromeda, just as the Milky Way itself was born from earlier mergers, just as Andromeda was born from earlier mergers. It's a story of continuous transformation, of matter constantly rearranging itself into new forms, of structures forming and dissolving and forming again. And we're part of that story. We're here now, in this brief moment of cosmic time, conscious and aware, able to understand what came before and what will come after. That's something worth appreciating. That's something worth celebrating. We're not just living in the universe. We're part of the universe becoming aware of itself, understanding itself, telling its own story. The final hour when Andromeda hits the Milky Way is still billions of years away, but in cosmic terms it's just around the corner. And when it finally arrives, when those trillion stars from Andromeda mingle with the hundreds of billions of stars from the Milky Way, when the gas clouds collide and new stars are born by the millions, when the supermassive black holes spiral together and merge in a burst of gravitational waves, it will be one of the grandest spectacles in the history of our corner of the universe, and maybe, just maybe, someone will be there to see it.